Now that we have described and spoken about atoms and how they are different from one another, we're going to start talking about now what happens when we start to combine these different atoms and to now create compounds. So a lot of the times there are different ways to represent atoms, and typically they're represented by these little spheres that you can kind of see over here on the right side. Different atoms will typically have a different color, and you can see here there are also different sizes based off of things that we're going to talk about. That is the orbitals, that where the electrons are going to be found, and these are simplified into spheres. And we'll talk about the more complex shapes those make in another chapter. But these are the standard schemes. So typically, if you see these different chemicals, these atoms are going to be, carbon is typically black or gray, hydrogen is white, nitrogen blue, oxygen is red, phosphorus orange, yellow, light green, darker green. So these are the colors that we'll typically see these compounds take. So if you see them in the future, and you'll see these ball and stick forms of these compounds, you might see that they're different colors, and that represents a different type of atom. So when we're talking about molecules, John Dalton, remember his theory was discussing that atoms combine to form more complex substances. Those are called molecules. And each of the different types of molecules, depending on their organization and the numbers and types of different elements in them, are going to give us different types of compounds. So oxygen, O2 for example, that is a molecule because there is more than one. Even though they're the same type, there's more than one of them within that molecule. Carbon dioxide, we have two different types of atoms. Ammonia, we have three. Sucrose, we have three, but there are big, long groups of these that are together. Looking at a 3D representation, these are just kind of where we're talking about when a molecule makes a connection or creates a compound. We're going to talk about different types, but these are going to be molecular compounds that are sharing those electrons. Remember I talked about that sphere kind of representing the electron cloud around the nucleus. This is a demonstration that these electrons are being shared by both of the different proton groups in the nucleus here. And so the same with the oxygen, nitrogen, and chlorine here. So that fusion indicates we have what we call a covalent molecule, or a molecule is fine for right now. And then the different colors, of course, we mentioned already, indicate different elements. And then the size of the spheres reflect that different sizes of the different atoms. And again, we looked at that periodic table trends, that worksheet. That is kind of giving you the idea of why we have different shells and they have different sizes, and those are reflected in these 3D representations. We also have the ball and stick model, where they don't have the spheres kind of overlapping, but instead we represent that sharing with these little sticks that represent electrons being shared. So there's a difference between the carbon in the middle, but then here's methane on the left, and then chloroform, where three of those hydrogens are replaced with chlorine. So those little sticks between represent electron sharing or bonds. So here we also, this is the space filling model, similar to the last one. It represents the different sizes of the atoms compared to each other, and we have kind of the fusion of these spheres within each other, representing sharing electrons. And it shows how these atoms take up space in a molecule. On the left here, we have oxygen and two hydrogen. That's water. On the right, that last slide with the ball and stick forms, we have methane. We have one carbon in the middle, and then 4 hydrogen on the outside of that. And then chloroform, remember we swapped 3 of those hydrogen with 3 chlorine atoms. So some different ways to represent the same kind of thing. This isn't very commonly used just because it's kind of hard to see where all the pieces are and what's all included. So now that we've been introduced to this idea of molecules, I want to start talking about the difference between pure substances versus mixtures. So you can have different pure substances as elemental compounds or molecular compounds, and we're going to talk about that. And as long as the composition is always the same regardless of the source. So this is an important part of, does it matter if it's water that came from dinosaur pee or it's water from rain? Water is the same no matter where it came from. So it's kind of a weird concept, but it's something that's important in chemistry to understand. It doesn't matter where it came from. So mixtures, they have different compositions. So they are typically made up of two or more substances. An example of soda, you have water, you have sugar in there typically, and you have carbon dioxide, maybe some flavorings. Though that's a mixture. That's a mixture of a lot of different things. And there are two different categories of mixtures: heterogeneous or homogeneous. You can also say heterogeneous or homogeneous. It doesn't matter. It's a potato, tomato, tomato kind of thing. Homogeneous mixtures are when the same properties are found throughout the sample. So liquid solutions, right, like our soda we were talking about, sugar, water, that would be a homogeneous mixture when you can't pull out, well, where's the sugar in there versus the salt versus the flavoring. It's all mixed together. Obviously, if you added ice, then that would be a heterogeneous mixture because you could pull the ice out and you could separate that out from the liquid. Gas solutions are typically homogeneous, where you would have a separation, or you can't see a separation between different types of gas molecules. For example, the air contains nitrogen, oxygen, carbon dioxide, other gases. You can't see them. It's all mixed together evenly. Another example is a solid solution would be different metal alloys or different steels, where you'd mix together compounds and you couldn't tell them apart once they're mixed together. Heterogeneous mixtures are where you could actually see different properties and different phases, different layers. You can see that here in the salad dressing, we have an oil and vinegar layer, and so those separate out. Ice and water, they have maybe this from the same molecules, but they're different physical states, so they are separated. And here's just an example of how this would look visually. Here would be the heterogeneous mixture on the right, homogeneous mixture where everything's more evenly distributed and uniform in mixture. So two different kind of ways of looking at mixtures. So remember, chemistry is the exploration of matter, and if we're looking at matter, we can have two different types of matter. They can be pure substances, or they can be mixtures of various compositions of different types of elements. We can separate these things always. If you have a mixture, there's typically a way to use to separate those out, and that's more what chemists do in the laboratory space. Once we have these pure substances, they can either be elements, so they're individual atoms, or they can be compounds. And you can do chemical reactions to change these from compounds to elements, or compounds to different types of compounds. So there are two different types of mixtures, homogeneous and heterogeneous, that have different types of properties, right? The homogeneous, it's the same throughout. Heterogeneous, you can have two different layers or phases, or you can kind of see bits of different chemicals within that. This should be a fairly simple activity for you guys. Just take this chart and fill out if you think that the chicken soup, ice, liquid soap, or table salt, if which of these categories it would fall into. Just put a check mark there in those spots and upload that answer. So I don't know how many of you are gamers or if anyone plays Minecraft or you have seen this before, but the idea of this world of Minecraft is that you have these little tables and you can basically put different elements on those tables, and you can create new things from that. So, for example, if you'd have maybe 3 pieces of some type of metal and a piece of paper, you can make a whey boat. Or you can make an Erlenmeyer flask with 3 different pieces of glass. So the idea is kind of the same, really. And it's an interesting concept because also you can't just put glass anywhere in here. You have to have glass in the proper orientation to create the proper thing. That's really the same. It's a really good analogy for real chemistry because you have to have the right types of elements and they actually have to be in the correct orientation to create the element that, or the molecule that we want to look at. So it's kind of an interesting idea. And so again, you have the iron oxide, you have this 2 to 3 ratio, but the iron and the oxygen have to be properly organized around each other to actually make that. So we're going to start looking at how do we talk about these things, how do we write them down. We need to look at what we use for chemical formulas. So this goes back to the periodic table. Remember, we have that chemical symbol, and we're going to use those now. So free elements like iron, sodium, neon, aluminum, these are examples given, right? Instead of writing out the whole word, we just use that chemical symbol. We just use that chemical symbol to demonstrate that we have that element and we're looking at it. Diatomic molecules, this is from the Greek word di, right? We have mono, di, tri. We'll talk about that in a little bit. But diatomic means 2 atoms, 2 atom molecules. And for example, we have oxygen, hydrogen, nitrogen, chlorine. These are all examples of some diatomic molecules. They share electrons. They create these covalent molecules that share electrons and are together. They aren't floating around individually, they float around together. The symbol for that, when we have 2 of these in a group that are sharing electrons, we put a subscript of a 2 here to say there are 2 of these oxygens in this group. There are 2 of these hydrogens in this group, 2 nitrogens, 2 chlorines. So they're combined. That subscript means that they're combined and it's part of that molecule and they're sharing electrons. Something that you're going to have to start to do is to be able to count atoms within a molecule. Now, if there's no subscript, that implies that there's only one of those things. So this carbon, there's just one of those in that group. There's one here, and one here. Now these parentheses tell us a little bit something about the number of things in that grouping. It's just like arithmetic. If I have this in parentheses and I have a subscript of 3 here, that tells me I have 3 of these CH3 groups. So it's carbon, hydrogen, hydrogen, hydrogen. There are 3 of these. So that's equal to this same thing here. 1, 2. Sorry, this is getting a little sloppy here. That is the same thing as these three sets of those. But it's just condensing it so you don't have to write that CH3, CH3, CH3. You're going to write it out over and over again. It just takes too much time. So we simplify that and put brackets around it. So you can do a couple of things. You can just know that, and you can multiply that 3 throughout, so you know that this is also kind of the same as C3H9 and then COH. So that can help you. The reason it's done this way is something you'll learn later in the semester, or if you take organic chemistry. It helps us organize these little groups, and it helps us recognize that they are coming off of, this is the central carbon. We're not there yet, but there's a reason for it that we're not going to get into quite yet. But now if we're looking at, okay, so now we know that's C3H9COH. Now we can kind of account for all of these different elements. And we're going to have, we look at carbon, we have 4 of these, right? I have 3 here plus 1 there. Hydrogen, we have 10 of these because I have 9 here and 1 here. And then we just have a single oxygen. So this is how we can start to do accounting. You're going to have to do accounting because remember, one of John Dalton's theories that still holds today is that you have to have conservation of mass. You have to have, if I take this molecule and I change it, I chemically react it to something else, I have to account for all of my carbons, all of my hydrogens, all of my oxygens. They don't go away. They just rearrange themselves. So counting atoms is the first step in doing more complex things in chemistry. So this activity, you get to practice some time working through some of the practice accounting of the different atoms. I'm going to go through the first 2 with you just so that we can be on the same page and make sure you're doing what you need to do. So for this first one, A, we have this sodium. So it's important that you can start to recognize the different elements, right? The letter of the element is always capitalized, and if it's the second letter, it's always lowercase. So we know that that's just one compound, it's sodium, and that subscript says that there are 2 of those. There aren't any other brackets or any other sodiums found in there, so the number of sodiums there are just 2 of them. This carbon here is alone by itself. There's just a C. There's no other ones there. It's just 1. This oxygen, remember the subscript behind is always behind that element that it's accounting for. There are 3 of those. So that's pretty easy, that one. B is a little more tricky because now we have brackets and subscripts. And remember, it's just like a mathematical equation. We have to multiply through that bracket with everything in there. So nitrogen is its own thing. This hydrogen is its own thing. And so we have to multiply that 2 through there twice. Remember, that means that we have NH4, NH4. That's what that parenthesis with the 2 behind it means. It means that we have 2 of these. So when we have a nitrogen, I'm going to account, okay, so we have actually 2 of these. 2 times 4 is 8, so we have 8 hydrogens. It's an inferred 1, right? There's nothing there, so we just assume that there's only 1. And then this subscript behind the oxygen is a 4. So I'm going to let you finish these off. Post your answers in our weekly content space. I'm going to start talking to you about molecules, and we already talked about how we can organize these in space and how we can draw pictures of them. Here's a ball and stick picture of a molecule. And we're going to start talking about now we have to translate this into a picture, into a molecular formula. So we can see we have molecules, we have these chemical bonds between the molecules, and then we can transform this into a molecular formula. Remember we talked about there was this method for, okay, these black balls are carbon. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that's this carbon 8 over here. So we can see that there are differences in, we can account for these things. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. The nitrogen 1, 2, 3, 4. And oxygens, we have only 2 of those. So we can translate these into molecular formula, and then we use that formula then kind of when we're looking at chemical reactions to help us understand maybe what's happening and to account for all of the elements in that molecule. Instead of drawing this out, sometimes you might want to just draw something out on a piece of paper and you don't have red or blue or green or whatever color you need. So instead, we draw these out and the atoms are attached with lines and those represent the bonds. So here's an example of water. We have H line, O line, H. So the same as H2O, that's water. Methane is 1 carbon and 4 hydrogens attached to the carbon. So this is methane. So this is a representation. This is how we represent atoms within molecules. And again, those bonds, those represent electrons that are being shared. We're going to talk about how that happens a little more later in the semester. Here are some examples of more complicated molecules: urea, CO, NH2, 2. So we can also draw this out or write this out. If I wanted to create this molecule of the carbon in the middle, I have an oxygen up here, and then I have an NH2 groups. So then you might have noticed I drew 2 lines over here. That's a special type of bond, a double bond. We'll talk about that later in the semester. But here I can recreate this using my this format where I use the atomic symbols rather than the balls and sticks to represent this organization. Molecular compounds occur and are formed when non-metals combine. So if we're looking at our periodic table on the top here, we can see these elements in blue are non-metals. So it's a really small version. It's a small number of things that we're looking at for molecular compounds. This is really the basis for organic chemistry when we're looking at just these non-metals. Some of them, so you can see here, carbon and oxygen make CO2, hydrogen and oxygen can make water. We have a few compounds that are only 2 atoms, HCl, carbon monoxide, HF, NO. So some of those things are just pretty simple. But we have a lot of really complex molecules: DNA, RNA, sugar molecules, different type of amino acids and peptides. All of these things are made with these molecular compounds and non-metal compounds. So in order for some of the simple binary molecular compounds, first we want to know which elements are present and how many of each of them are there. So an example of this, so again, we want to translate this name clearly into a molecular formula. So we want to be able to name something, and then someone can hear that name and be like, oh, this is how many, this is what types of atoms are in there, and these are how many of those atoms are in there. So the first part of this element is always the English name of that. And then the second element, we use the stem and add the IDE to the ending. So let's, and then we use Greek number prefixes to specify how many. The Greek prefixes that we're going to look at: mono, di, tri, tetra, penta. And then hexa, hepta, octa, nona, deca. So these are 10 prefixes that are going to be pretty commonly used in chemistry. So here, the first element, second element, use the IDE ending. Let's do an example of this. So if I have hydrogen chloride, that's going to be HCl. Phosphorus pentachloride. Phosphorus is the English name. And then the second group has 5 of these, so I use that Greek prefix penta for 5 in the name. If mono is always omitted from the first element, so you might have wondered, why doesn't it say monohydrogen monochloride? Sometimes those are submitted because it's just, then it's assumed that, okay, if hydrogen chloride, if there are equal numbers of them together, we're just going to omit that first one. So we don't always have to put mono in there. And again, mono is often omitted in the second element unless more than one combination of the same 2 elements exists. So for example, carbon monoxide, we use monoxide because there is also carbon dioxide, which is present and readily available. So if for example, carbon dioxide didn't exist, then we wouldn't use carbon monoxide. There's no hydrogen dichloride, that doesn't exist. So because that doesn't exist, we don't use that name, monohydrogen monochloride. Another kind of note, when the prefix ends in a vowel similar to the start of the element name, drop the prefix vowel. So we don't say monoxide, we just say monoxide. Here is another learning check that you should submit the answers to. I'm going to go through just the first one again to give you a little bit of help to just to make sure we're on the same page. The prefix and then the element name, prefix, stem, IDE for the second one. So what you're going to have to do is probably get the periodic table. If you're not comfortable or familiar with some of these elements, this is a good way to practice that and to get used to the names of some of these elements. So this first one, AS, is arsenic. So there's only one of these, so I don't need to put a prefix in there. It's just arsenic. And then we have the fluorine here, but I'm going to drop the ene part and add an IDE ending, fluoride. So arsenic trifluoride. That's the answer for that one. Arsenic trifluoride. So I'm going to let you guys do the rest of these. Just keep track of the names and follow the rules, and then you should have no problems. Back in, I believe, the early 2000s, there was a student that found out that this compound was very present in our environment and moved to ban this from use in the schools. And so he led a petition, and I believe he got the petition to pass. So this was banned. I don't know if it was in his city or in his school, but it demonstrated the ignorance of the population to some extent. So I want you to take a second, dihydrogen monoxide. Dihydrogen monoxide, based off of what we just talked about, what does this mean? What is that molecule? So draw that out and upload your answers in the discussion board why this is kind of a silly thing to worry about. Now that we've had a chance to talk about some of the typical naming for binary molecules, now I want to talk about exceptions to that. So when we're looking at something that is a nonmetal and hydrogen, we usually don't use any prefixes because we get the number of hydrogens from the nonmetals, from the periodic table. So there's a formula, we can kind of look at that, an example, and we're not going to get here right now, but based off of where sulfide is, or sulfur is on the periodic table, we know that 2 hydrogens will be attached to it. We'll talk about that in a little bit here. The same here with telluride, based off of where it is on the periodic table, we know that we're going to add 2 hydrogens on there. So we don't say dihydrogen telluride, monotelluride. It's just kind of, it's recognized that with hydrogen, how many should go onto that element. So the way that we can do that is by looking at the right side. Remember I said the right side of the periodic table are where most of the organic compounds are, where the things that we talk about in organic chemistry that relate to life and the things that are found on Earth. The elements, the fluorine, chlorine, bromine, and iodine, those are all on the far right. Of course, there's 8A, which would be all the noble gases. Well, those don't interact with anything else, so they're not going to be attached to hydrogen. But you notice what is happening here is we have 1 hydrogen attached here, we'll have 2, we'll have 3, 4, right? So this is a simple hydrogen comparison for the nonmetals, and this is why we don't say carbon trihydride or something like that, or hydrogen trihydrogen chloride. We don't do that because there's this systematic way, there's this regular organization of how many hydrogens would be on there. So we don't write out those formulas telling us how many we have. So molecules containing nonmetals and hydrogen, we just take the number of hydrogens that combine with the nonmetal versus the number of spaces from the noble gases. So for 7A, we have 1 space, so there's 1 hydrogen. There's 1, 2 for oxygen, sulfur, selenium, telluride, so that we have 2 of those. An extra one, we add another hydrogen, another further, we add another set of another hydrogen. So that's kind of how we do that. And you can kind of see the number of hydrogens relates to how many spaces away it is from the noble gas. There's an international way that we look at naming, and it's this kind of this nomenclature system. Obviously, there are things that existed on Earth before we created this nomenclature system. That was very common that we had names for already, like water and sucrose. So we don't use this naming system for those things because these things were around before we had the naming system. And it's just too hard to ask other people to change the names. Ammonia, phosphine, those are all things that we typically don't use the mononitrogen, or we don't say nitrogen trihydride, for example. Phosphorus trihydride. We don't do that. There's called ammonia, phosphine, because they exist here already before this naming convention came out. So I want to go into some of the naming of organic compounds, because we're going to get into some of this and introduce this idea this semester. These are things that are commonly found in biology and biochemistry, so it's worth kind of describing this. Carbon compounds typically contain carbon, hydrogen, oxygen, nitrogen most of the time. About 96% of life contains just these 4 elements. Then, the other 3 to 4% are all of the other elements on the periodic table, but a vast majority of life is made up of just these 4 simple elements. So originally, we thought that these compounds only came from living organisms, but now we know that they're more general. They are part of a lot more elements as well. And that's why we got the organic kind of thing. That's why we have from organisms, but now we know that these are more abundant than just living things as well. Hydrocarbons, they're the simplest type of organic compound. They only contain carbon and hydrogens. And here's an example of some of these. And I'm sure you've heard of some of these: methane, ethane, propane, right? You can have a propane tank to, do a lot of grilling out, butane. So these are all things that you may have heard of before, pentane and hexane. So they're named based on how many carbons are associated with them. Other hydrocarbons, alkenes. I talked about double bonds. Remember, I talked about that in a previous example where I drew out a double bond. These are when we have, instead of single bonds with the alkanes, we'll have double bonds with alkenes. Alkynes will have triple bonds. And we can have other functional groups here. If you remember the how that works with these balls, this would be an oxygen. And so when we have an OH group, oxygen and hydrogen, on a molecule of carbon, that will form a functional group called an alcohol. And if we add an alcohol onto a methane carbon group, then this creates a methanol. If we had an ethane and we add the alcohol group, it's ethanol. Propane, it's propanol. Butane, butanol. So that's kind of how we name some of the simple organic compounds. So these are the classic building blocks of organic chemistry and the starting point for talking about organic chemistry. So now there's a difference. So we've discussed molecules, and molecules again are sharing electrons. So there is a sharing of the electrons in the outside of that atom. And we're also going to talk about ionic compounds, where there is not a sharing of electrons, but because of how they're set up, they're actually charged compounds. And they actually, because one is negatively charged and one is positively charged, they're attracted to each other. So they have this attractive force, but the electrons between the atoms are not being shared. So let's look at this more closely. These on the sodium, and we have a chlorine atom. And these little spheres, this is what we call shells of electrons. But sodium originally we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These blue balls in the sodium are 11 electrons. And if you look on the periodic table, sodium has 11 protons. So right now, as this is shown here, this is a neutral atom. But what happens is, because you can see this circle here is really kind of far away from the nucleus. And sometimes that electron, because it's so far away, remember, we have a positive shell here in the middle. Remember, this is positively charged. And these electrons are all negatively charged. These are all negatively charged. And if this leaves, we take a negative charge away, and then we're left with a positively charged sodium. And this, you'll notice also, this outer shell is now empty. And what happened if this chlorine is close by, the electron moves over and it will fill up this open spot. And the chlorine then takes on a negative charge. So now we have a positive charge and a negative charge, and these are attractive to each other. And so then we can form this ionic compound, where these are ions because they are charged. And now this is an ionic compound when we have positively and negatively charged ions. So one thing just to also note, cation ions are positive, anions are negative. Just some nomenclature for positive and negatively charged things. So how do we know if something is an ionic compound? So one of the things that we can do is ionic compounds will conduce electricity, because remember what's happening we have this open space in this sodium molecule, and electrons can jump into this orbital and hop and pass through one sodium to the next, to the next, to the next. So we have this open space, and if we are in a group like this, if we have sodium chloride as table salt, essentially, and if I have some table salt on my counter and I want to put an electrode through that, it's solid. These are all kind of evenly distributed, so we have these little tiny sodium ions in between these chlorine ions. The charges are evened out and distributed, and there's no movement. There's no ability for electrons to jump from this sodium to this sodium because they're too far away. However, so you can see that here, if I make this a solid sodium chloride and I have a battery hooked up to a light bulb in solid sodium chloride, I get no light turning on. But if I melt this, if I make molten sodium chloride, so I have to heat it up really hot, and it melts, what happens is then we can have the sodium ions can move around and interact with each other. So if there's an electron, they can bump on one sodium and it can push to another, and they can get through this space to turn on the light bulb. If I have pure water, no electricity conducts through pure water. So you might think of like, oh, I've always been told, I shouldn't be in water if it's lightning. Well, typically you think about that, or you don't want to go swimming. The reason for that is because most water that you would be in wouldn't be pure water without any ions in it. If we put some salt in there, that'll allow these electrons to flow through through those open orbitals. So I'm going to show you this kind of little image here. If we're going to allow this to work, this electron's kind of bumping through that sodium, and you can kind of replay this a couple times. That's kind of the idea. And the only way that electron is able to kind of bump through this path to get from this negative to the positive element here is if it's molten, so that we can have the sodium moving around and bumping into other sodium ions, or if we have it in a liquid solution and they are freely able to kind of move around and touch each other. Otherwise, if we're in a solid solution, those are too far and there's no movement, and so we can't have that electrical conductivity happening. The last example was of an ionic compound, but let's look at table sugar. So this is the molecular structure of table sugar. This might look a little different because I have this 6-cornered molecule, and really we don't show this. The carbons are on the corners here, but we'll talk about that later in the semester. But this is a molecular compound where electrons are being shared. If I put this in solution, there's no ions, there are no open orbitals for electrons to jump on. So if I take this and I put table sugar in this solution, even if I have a battery hooked up, there's no electrical conductivity because the electrons are all shared and accounted for, and they don't leave that element. There's no open spots for it to jump. So the difference between an ionic compound and a molecular compound, or molecular compounds don't fall apart, and there's no room for electrical conductivity, or ionic compounds do fall apart. They don't share their electrons, and because of that, there are typically little holes for electrons to flow through and to activate, for example, a light bulb, or allow for electrons to flow through them. So how do we know if something's going to be an ion? The periodic table of elements helps us to predict some of these ions. So if we look at the periodic table, hydrogen's typically going to be a +1. Remember, this is just one proton, so it really can only be a +1. And you can see, remember in the periodic trends idea, the reason these are put into families because they have similar characteristics. These in 1A will typically only like to lose 1 electron. In 2A, however, they'll typically be able to lose 2 electrons. 3A might lose 3, 4, and then they get a little more weird. We go back to 3 to 2 to 1. So these are some of the negatively charged elements that we'll see in the periodic table. Remember that this isn't showing you, these are the 2A, those are the tall groups. So maybe compare this to a periodic table to see where aluminum, carbon, nitrogen, oxygen, these are, the reason this switches over is where more on the right-hand side of the table. These are the non-metals right over here. That will be negatively charged versus the metals are going to be positively charged. So now we're going to talk about naming ionic compounds. And the first is similar to naming molecular compounds. You get the English name and then a number if necessary that tells you the charge state. And we'll talk about that in a second when I give you some examples. And then the anion is the second, this IDE ending. So the cation is going to be the metal, anion is going to be the non-metal. So these are always, ionic compounds are always metals and non-metals combined. So here's some examples of this naming system. We would have potassium oxide. So we have potassium as the full name. We don't need a number. The number isn't related to how many potassium are found here. It's related to if there are more than one charge state for that potassium. But potassium's in that first column of the periodic table, so we're not going to, it's only +1. There's only one option here. So if we go to down below, something else I should point out is sometimes you're going to have polyatomic groups. So these are actually groupings of multiple groups here, and typically they will be, so you can see NH4, ClO3, they're actually groups of nonmetals that will form ions. So these have their own names. We have ammonium, and then we have the chlorate. So that is, these are a little different and unique. So that's a little bit of an example of the difference. Chromium-3, this is telling us, remember the chromium here, but you say, hey, wait, there's 2 of these. We're going to talk about this in a second, because the chromium will actually have a +3 charge associated with it, and then the oxide. And so these numbers represent how do we get a neutral molecule. There's no charge up here that's saying this grouping is neutral. There's no overall charge when we have 2 chromium and 3 oxygens. And then finally, the example of zinc bromide. Notice I just zinc bromide. I don't have zinc 2 bromide or zinc bromide 2. And this is because we only have one type of ion for zinc that's typically made. Metals that form only one positive ion, those are examples. We're going to go through some more examples just to give, that was just to give you an example. But we only have, the cation is the English name for the metal. So Na plus is going to be sodium, Ca plus 2 plus is calcium. But sometimes when there are more than one ion, then you would put that number behind it. So chromium 2 versus chromium 3. The number relates to the charge state. The number does not relate to how many atoms are in that molecular or ionic compound. It's just related to the ionic state of that element. So here's a table of some of the typical negative ions that can form. Hydride, so hydride, typically we think of the hydrogen ion as being positive, a proton, but it also it is possible to have a hydride anion. Carbide, silicide, nitride, phosphide. So this IDE ending tells us something about that it's a negative ion. So anions, we're going to use the monatomic anions named by adding that IDE element at the end. The transition metals are always a little more difficult because those although they're much less reactive than group 1A and 2A, they do still transfer electrons to nonmetals to form ionic compounds. And the number of electrons is less clear in the transition metal area or the post-transition metal area because they have different properties that we'll talk about later in the semester, but it's less easy to know that or to memorize that. So just examples of these, you can see that titanium has 3 different ionic forms, chromium 2, manganese has 2. So a lot of these will have a couple of different ones. And you'll notice that some of, I just have this little chart below. These will typically be some of the charge states that these will form. So copper, for example, is really going to typically be a +1, but it can be a +2. Silver will always be only a +1. So these are underlined. The gold will be typically a +1, but can be a +3. So underlined ones can be other forms, but more typically like titanium is going to mostly be a +4. Although it can be found in the other forms, this is the primary state. Tin is typically going to be a +4, not a +2, although it can be, and so just examples of that. Here are some, I mentioned polyatomic ions. This is a list of polyatomic ions. I'll usually, again, give you this list on a quiz or exam, but it's worth you looking at this and being familiar with it so that when you can see this, you can minimally, again, you don't have to memorize all of these, but the better you know them, the more easily you'll be able to recognize these names and to recognize these groupings, and it'll help you with the speed at which you can do some of these things we'll be doing in this class. So some of these you may have heard before. Ammonium ions, this is a polyatomic grouping. These are nonmetals that group together and form a positive charge. Hydroxide, I'm sure you've heard of that. Maybe cyanide ion, Cn minus. Nitrite, nitrate. So you'll notice there's an ITE versus an ATE ending. So usually that refers to the number of oxygens here. We have chlorite, chlorate, perchlorate, permanganate. They all have oxygens in them. We have negatively charged compounds. Carbonate, sulfite ion, hydrogen sulfite, sulfate. So we have these are all different phosphate groups. I'm sure you've heard of as well, potentially. So these are all groupings of nonmetals typically that can form, with the exception of mercury, this mercury ion. These are mostly all nonmetals that form together as multiple groupings of nonmetals that will sometimes form charged state ions. So just a little side note, something that might help you kind of think of something's a nitrite versus nitrate. This ATE suffix means it's the larger number. So you can kind of think of, like eating something. You'd rather eat the larger number than the smaller number. I don't know. Just the sulfate versus sulfite, nitrate versus nitrite, chlorate versus chlorite. You'll notice that the number of oxygens in those are with the ATE ending are larger. So just if you ever need to know, but it's really worth taking note of that, because I've had people make the wrong solution because they were supposed to, for example, make a chlorite solution, and instead they made a chlorate solution, and then the chemistry doesn't work because you picked the wrong solution. So it actually really does make a difference. Hopefully you have your notes with you, and what I'd like you to do with this last slide here is to go through this, try to figure out what this ionic formula would be. Write that out and upload your answers to our discussion board space, and that's going to end this part, and then this will be continued to talk more about ionic and molecular compounds